Our first presentation, as I've said, is static analysis for Synergy code, smarter scanning, better code. Our first speaker, Oliver Chu, joined Synergex in 2019 as a member of our Synergy compiler team. He has made numerous enhancements to the traditional and Synergy.NET compilers and has collaborated on code analysis projects, most recently contributing to our eagerly anticipated static code analysis tool. Oliver is going to tell us about this tool and how it can deliver helpful insights to your team.
Hello, everybody. Welcome to Static Code Analysis for Synergy. My name is Oliver Chu. I've been working here at Synergex for about 5 years. I work on the compiler team, but I also work on the code analysis and information tool, aka CATE. And we're going to see how this static code analysis program can help you with your DBL code. Before we get into what static code analysis is, let's take a look at security vulnerabilities. Now, we're going to talk about OWASP vulnerabilities. The OWASP Foundation is a nonprofit that stands for Open Worldwide Application Security Project. They publish a list of the top 10 security vulnerabilities for applications. And they also publish a different list which has additional vulnerabilities that you may be interested in. Now, these vulnerabilities contain things like freeing a pointer twice, cryptographic failures, and security issues with certain programming languages such as Java. And you might be wondering if these vulnerabilities apply to Synergy DBL code. And yes, they do. As a business, you may be interested in SOC 2 Type 2 compliance. SOC 2 Type 2 is essentially when a separate entity looks at your business over the course of 6 to 12 months and looks for things like security, availability, processing integrity, confidentiality, and privacy. SOC stands for System and Organization Controls. Now, if you work in banking, finances, or really any other business that has an important need to serve customers with their software, you will need to be careful about security and protecting your customers' data. So these security problems are really hard to fix manually, and hackers are essentially anonymous on the internet. They can go into your system and exploit these weaknesses. Damage to software infrastructure can occur. People can install malware, ransomware, other things. They can steal your data, expose it to the world, and cause serious problems. Your businesses can go broke, they can go bankrupt because of this. So how can static code analysis help us? Well, for static code analysis utility, what we want to do is analyze your program without actually running the code. What is the point of this? Why can't we just use the code at runtime to tell what the problems are? Well, static code analysis has several advantages, actually. So the fact that we're not really running the code means that we are in a completely safe environment. We can't touch the database. We cannot access the files on your system, and we cannot expose sensitive information such as social security numbers, phone numbers, names, and such. So what we want to do here is that even without running the code, we want to find all the values of interest that flow through the program's logic. Now, by program's logic, I mean like if statements, while loops, passing arguments to functions, using parameters, returning things, things like that. And we want to basically trace them to find endpoints where there could be security flaws from where the data starts being passed around to where it ends up, where it ends being passed around. And this is not the only thing that static code analysis is good for. For example, you can use static code analysis to detect unused routines that you never call in your code because things have changed over time in your source control such that you don't need the routines anymore, but they're still defined in your program. Now, since we don't use the traditional Synergy runtime DBR or the .NET runtimes, in order to find these flaws in Synergy code, we can instead try to make good guesses about what the code might do at runtime and find issues with code quality and other things such as code smells. A code smell is basically a problem in the code that is not actually a bug, but is indicative of a deeper problem with the design of the system. You may have heard of static code utilities that are already being used for other languages. For example, SonarQube. SonarQube is a utility which you can run against a lot of different languages, such as Java, C#, JavaScript, and Python. Now, we want to do the same thing for Synergy code, and that's what we've been working on. In fact, one of the ideas is to turn our program that we've been working on into a SonarQube extension, so you can use it alongside the SonarQube capabilities for C#, Java, and so on. So, what are we really looking for in Synergy that is specific to Synergy? Well, there are a few routines and statements that could be problematic that have been used across the years. So, for example, spawn. Spawn, the first argument to spawn can be used to run OS programs. For example, if you're on Windows and you want to open Windows Explorer, the name of the Windows Explorer utility is just Explorer. If you pass the string Explorer into spawn, then your Synergy DBL program will open Windows Explorer. Now, shell is very similar, and the second argument to shell will be the command to run on the OS. So you can also use this to do various things on the current operating system. And on Linux, it's kind of similar. The commands will be different, but as long as the string is well formatted and it's a proper command on Linux, then of course you can also run commands there. So one more thing is open. Opening a channel is extremely common in Synergy, right? You open a channel, you want to write some data, read some data, or open something for the console. Open is a security vulnerability as well. Why? Because the command could be a vertical bar followed by another string. And when you do this, then what happens after the vertical bar, that's treated in the same way as spawn or shell. It's a command to be executed on the current operating system. So how can hackers take advantage of this? How can they get into your Synergy code? Well, normally they can't do this, right? If you control the program, you wrote the program, you know what it does, you know the inputs and the outputs, how can they possibly mess with this? Well, what about external input? When you read a file, when you read a database, if you don't control that file or you don't control the database, then you could get some arbitrary data in your program. Normally this program would just process the data like any other data. But what if instead of the names of your customers or their phone numbers, that for some reason there's a piece of code embedded into the database, or the string you read back is also a piece of code? What happens then? Here's a comic. This is from the webcomic XKCD. And we have a mother here who is calling her son's school. And the school is concerned because the mother has named her son Robert Drop Table Students with a bunch of punctuation marks in the name itself. So what does this mean? It means that his first name, Robert Drop Table Students, has been embedded in a string that will be executed as SQL code. SQL as in structured query language for databases. So when this happens, when you concatenate the strings together, what happens is that drop table students is a command in SQL that will delete the table of students. So that means the school just lost all their years of student records. And so this is funny because a mother would not actually, name her son this, but it doesn't have to be a real name, right? So a customer using a web form, you may ask for their first name, their last name, their address, and their zip code, and so on. They don't have to put numbers or letters in those fields. They can put strings of code and just somehow hope that those strings of code will eventually get executed. And this can actually happen. This is called a SQL injection, and it does apply to Synergy as well. So we want to look for these things. So what are the sources of dangers? We already covered this a bit. So any file that you don't fully control, you downloaded the file, or you grabbed the file from somewhere else on the internet, you don't know what is in the file completely. So if you don't know what's in the file, how can you be sure that it's not going to eventually end up in your Synergy program? Once it ends up in your Synergy program, are you careful enough to not call spawn or shell on part of that string or the entire string? Again, values from the database. When you update the database, it's usually because you're updating it with customer data. Again, their own information. If the customer is malicious and is trying to break your system, then they can type bad values into that database, which can mess with your program. So also typing into a form or the console, if you're reading just data from a terminal or a console, that can also be a problem. Finally, EXIF parameter. So EXIF parameter can be safe if you fully control both the server and the client. But what happens if you do not control both sides? Well, values that come from the server can be considered dangerous. And in fact, what we do in our static code analysis is to say that essentially all the EXIF parameters could be sources of dangers. And we're going to look for where those parameters get used, where they get passed, and where they end up in order to tell you, does it actually end up in a bad place, like a spawn or shell call, or does it get sanitized properly and be treated like any other piece of safe data? So what is tracing? So what are we doing during tracing? I keep talking about how we want to see where things flow. So the variable, let's say, you have a variable called temp, and it is assigned like 3 different strings. So we want to track those strings. Now, since we're not actually running the code, we don't know what the variable is yet, right? It could be any of the 3 strings because you have multiple assignment statements that are including that variable. So we just consider all 3 at once, and then when they get passed into a function, we consider what happens inside that function and how those strings are manipulated, and we determine if there's a problem in that function. But if the function passes the data to another function, or it returns it, or it writes it somewhere, or it passes it through a channel, then we have to consider that too. So we consecutively consider all the possibilities over and over again and see, from the starting set of values on that variable, where does that variable go? Where is it used? And when it is used in any of those other functions, is it a problem when it's used? Is it dangerous? Is it not treated correctly? Is there some sort of loss of data happening in the middle? Those are things. Those are the questions we can ask, and we can answer some of those questions using static code analysis. So it doesn't just apply to strings; it applies to numbers. Numbers are important because they can be used to, index into arrays. What if you index past the end of the array? What if you index past the end of some data? What if you use a ranged reference? So the numbers that are involved in the range, if the both parts of the range are variables, then depending on those numbers, the output could be different. We consider that when we do the static analysis. So here's some concrete examples. So the function on the left here, it says no danger. We're just returning a string called no danger. It doesn't look like an OS command. It doesn't seem to be a problem, and it really isn't. So this function is 100% safe. It's not reading from a file. It is not accessing a database. It's not using a web form. It's not making a web request or anything. It's just a normal function you wrote, you fully control it, and you know exactly what the output is going to be. So this is fine. This is good code. The function on the right, however, is a bit more complex. It has an if statement saying that if there's a condition that is true, then we're going to assign some data into a field. Now, the first part of the true case of that condition is fine. You're assigning some known string literal into a field to initialize that field. However, the else case is not okay because you said console.readLine, which means you're reading an arbitrary string from the console. You're storing it into field, and then you're returning it. So it's not really obvious that other function call could be dangerous, but it is, right? Because you don't know what it's going to return in case the condition was false. And once you return it, where does it go? So you may use other function call in 100 places. Then you would have to manually check those 100 places. But not only that, each of those 100 places, where does it go after that? 100 times 100, right? Because as you go along in the code, it can be very hard to track down where the data is eventually going to end up. And so you get sort of this like exponential growth where it's going to be infeasible to check all the cases manually. And that's why we want to automate this. All right, and what about out and in-out parameters? So Synergy is interesting because we give you a lot of flexibility with the parameters, right? So an out parameter or an in-out parameter means that when I pass this parameter, what happens is that you give it the variable, and then I do something with the parameter, but I can also assign to the parameter or change it in some way. And after the subroutine returns, the parameter has been mutated, even though there was no return value for the subroutine, right? So it's a less obvious way of changing a variable. If you have a function call, it's very obvious. Return value equals function call, and then the arguments to that function. It's obvious that the data is flowing out of the function and into the variable or the destination that you're storing it into. But here it's a little less clear. And being a little less clear is important because humans reading the code think that when you pass something, most likely won't get modified. However, if they don't check the subroutine definition, they won't know whether it was an out or in-out parameter, and maybe it is getting modified in the subroutine. So once the subroutine returns, there was no return value, but the parameter has actually changed. The variable you passed in has actually changed. Now, when that happens, it's very hard to see as a human, because when we read function calls, we don't expect random arguments to change, but they can. It all depends on how you declare the parameters. So the advantage of automating this is that it's harder to miss these, right? We already know which parameters are out or in out. We can detect them just like regular function returns, and we can process them in the exact same way as function returns, meaning that the human reading the code doesn't have to think about, is this argument being modified? Is it in out? Or is it just read-only argument? Another complication in Synergy, we have overlays, ranges, and essentially field position indicators. So here in this example subroutine, we have a record called all and another record called other, but other is overlaid on all because of the comma x. So when we do console.readline and store it into field 2, then what happens to the other record is that the second half of the record is essentially changed to whatever the user wants. Then we spawn a field. So initially this looks okay because they're separate records, and a field is not part of the second record. But really it is because it's overlaid. They refer to the same block of memory. So when you spawn a field, you're actually spawning the entirety of the other record, and the second half of the record is controlled by the user, potentially the hacker. Even though they don't have power over the first half, who knows what they could do in the second half? They can be very crafty and turn that into some sort of command that would damage your system. I talked about field position indicators. So there's an @ sign you can use to indicate the position of a field. You can position it inside the record. There's also relative ranges, absolute ranges. You can do an assignment statement into a range. So all of these powerful features are complicated to track down, right? Because it's not just the variables. Oh, I see this variable assigned to that variable. I see this variable returned from this function. Yeah, it's also slices of variables. I can slice this variable. I can slice that other variable, then change the slice to something different. And then I can move the fields around in the record, indicating where their absolute positions in the records will be. It's really hard to tell at that point which part of the memory is it accessing. So we're trying to make our tool smart enough so that if you range a section of data that is not dangerous, even if the section that wasn't ranged is dangerous, then we sort of say, well, this part is safe, that part is not. And it could be the other way around. You could be ranging a part that is dangerous and then ignoring the part that is not dangerous. And so we would consider those two possibilities. That part is dangerous, and then this part is not. So a lot of complicated overlaying fields. So you don't want to do this manually because it will be too hard. And not only would it be too hard, if you attempted to do a full analysis of all your programs and this, then what will happen is that you will miss some things because humans are good at making mistakes, and you will miss a bunch of things. And then if you miss a few things, then you're not actually secure at that point. So combinations of everything. So it's not just overlays and ranges by themselves. It's not just in-out parameters by themselves or return values. It's all the possible combinations, everything that's strung together in a real application that does business logic. It gets extremely complicated. So we want to find all the possible paths from the danger source, such as read-s or readline, into danger sinks such as spawn or shell. So read-s, spawn, shell, those are super specific things, but we can be broader. So the size and scale of legacy code, we can detect a lot of things with static code analysis. Not everything is implemented yet. We are still working on it a lot, but a lot of the vulnerabilities in the OWASP list, they have a great variety in what they have, but static code analysis can find answers to many of them. And for those that are harder to answer, we can approximate a solution for you. We can try to give you helpful hints, even when we can't find the exact answers, so that you will have an easier time fixing these kinds of problems. So you may also want to consider the opposite situation where instead of the hacker trying to inject some data into your system, you are trying to prevent your own data from leaking out, right? So your own data, by leaking out, I mean what is happening is that the hacker gets into your system, they just read the data, and they don't do anything else. You can't see anything happen because nothing was damaged. There were no deleted files. Your database looks exactly the same. And what they have stolen is information, really. They know something about confidential information that you're keeping around that you're not supposed to be giving to the outside world. And this is also a situation which we can apply the static code analysis to, because since we are tracing all of the data, what is happening is that we can tell when it gets dropped outside of your program. And that's also very, very valuable. So let's automate it. All right, everybody, it is time for the live demo here. What I have here is our code analysis tool right here. So what I'm going to do is I'm going to run a test in the background, and I'm going to tell you about a security issue that I purposely added in some legacy code. So let's do that. So I'm going to right-click this and run this test. And while this is happening, we're going to switch to a different window and talk about some legacy code. So let's walk through an example of a security vulnerability. So here I have a starting point called console.readline. So we've seen this a lot in this presentation. It doesn't have to be this. It could be a read-s. It could be something totally different, like reading from a file. But for now, console.readline will take a string that the user typed into the console and give it back to you. So this piece of data, we don't know what it is. It's getting returned from this function. Now, this data is going to go through another function called string identity. And this function is defined up here. And you will see that this function, what it does is it takes the parameter and it assigns it to a temporary field, and it just immediately returns the field. So what's happening is that the data is going into the parameter, going through an assignment statement, and then exiting this other function. So this function doesn't do anything with the data. It just passes right through. So we can keep going. We still consider the return value of this whole thing to be dangerous because it is unknown data. So we assign this to field. Once we assign it to field, we return 0. So of course, everything's fine. Not really, because even though it looks like this is safe, that it's just returning 0, it's not doing anything with field. This field is not part of a regular record. It's part of a global common. So this global common is connected to an external common, and that field's data can be passed through that external common into somewhere else. So where is that somewhere else? Well, we have to look at a different file in the same customer solution, which is this one. So we have a much bigger subroutine called DSP image here. And what this has is at the bottom of this data division, we have that external common. So we have an external common, which references the data from this global common. The field is right here. So the data is now in this field. And we assign this field into DSP wind. And this is the name of a record. In fact, you can see this record up here. This is DSP wind record, and it contains an unnamed A15 field. And now, where does this go? DSP wind, where is it used? So we're going to have to search for where is it used. And we see two problematic areas. So inside this if statement, we have an X call, spawn of DSP wind. So that data that came all the way from the console read line right here is now going into this spawn, which will execute on the current operating system. And next, there's a different one, which is also an if statement, shell with the second parameter as DSP wind. This is also a problem because it came from here. We don't know what it is, and now we're executing it. So this is not an actual security issue. I just put this code in. I fit it into the existing legacy code to for the purposes of this demo. But you can see that if you wanted to do this manually, would you notice this stuff, right? Would you notice that this is connected to this other file and is eventually being passed to spawn and shell down here? Well, now I'm going to switch to the other window, and we're going to look at the results of the test. So here, I'm going to scroll all the way down, and the test has finished. It has passed. I'm going to open the test log here, and that will give us all the data that we've collected. So the stuff at the top is not really that important. We want to go all the way to the bottom, and look at the trace paths. So here's the real output from the static code analysis utility. This is the format we have currently. It might not look like this in the final step when this becomes a real product. What we want to do is either have it be integrated in SDI, or we would want it to be some sort of SonarQube extension. So this won't be the final format, but we try to make it as neat as possible so that it is at least understandable for the purposes of this demo. So we start, where do we start? We of course start with readline. It's a source of danger. It tells you in this description that the readline is a source of danger, and it will show the current routine we are in, which is named DSP image function. And then it will highlight using these caret symbols, the console.readline, which is here. It's being passed as an argument. Then we just go through the rest of the steps. So we called it, and now we are passing whatever was returned from readline. It is going into parameter number 1 of string identity. So that's the name of the other function. The other function is highlighted as well. We go down here. Inside the body of string identity, we assign the parameter to temp. That temp field is then used down here. We return temp. Where does the return go? Well, we have to go outside of the function again. We see that the return value of string identity is assigned to field, and you can even see it up here in the description that it's assigned to field, and we still have the current routine displayed. Here, after going through that external comment, field is assigned to DSP wind. And now we get our endpoint, which says, well, you just passed this into spawn. So now we have untrusted input, which has reached the first parameter of spawn. And that's the vulnerability we're looking for. Now there's a second path here. This one is almost exactly the same. The only difference is that at the very end, it shows a different one. So this one is shell. This one points out shell, that untrusted input has reached parameter number 2 of shell. But in the first one, it's going to be spawn. So that's what it looks like. We're going to get back to the presentation right now. That's what I want to show. All right. So let's talk about a few things that we are planning to do. There is everything we've talked about so far is called related data flow. So related data flow means looking at assignment statements, return values, in-out parameters, ranges, overlays, and those kinds of things. But the thing it doesn't consider is conditional guessing. So what I mean by that is control flow. So if there's a condition and it could do one of two things, what related data flow will essentially do in that situation is to consider both branches of the condition, saying that we don't know if the condition is true or false. And that means that, well, if we don't know if it's true or false, then we have to say it could be true and it could be false at the same time, sort of. So we consider both possibilities. And then once we do that, we look into whatever function calls are in the first possibility, whatever function calls are in the second possibility. Then we continue the situation where we go into the function call, look at those things, and basically keep going for all those statements. But it doesn't try to do anything with the condition in this case, right? You're just saying, if there's a condition, just take all the paths and we'll figure it out later. But we don't have to do it this way, right? We can actually guess what the condition will be. Now, sometimes it may not be obvious at all what the condition will be, and in some cases, it may be impossible to tell what the condition will be without running the code. But we can make some pretty good guesses, right? So if the condition is more likely to be true, we can inform you of that, and that may be valuable information. If the condition is more likely to be false, then we can take that into consideration during the trace. There are two examples here. So one of them is subroutine always throw, and on the left, you can see this subroutine always throws a new exception. And after that, it calls spawn of some dangerous data. But the fact that you already threw an exception and don't have anything in the middle there means that you just cut off the rest of the subroutine, right? So technically, the X call spawn, that can never ever happen because throw is unconditional. It's not wrapped inside the if statement. So once you do it, then the subroutine's cut off. You don't do any of the rest of the subroutine, and you're actually safe in this situation. So if you're actually safe, you may not want to know about this because the thing is that we could detect a lot of different things, like let's say tens of thousands of things, And for the things that are actually safe, you may want to omit them. Now, I think at the recent Synergy Summit, one of our customers mentioned that, what if we want to see everything? What if we don't care if it's unreachable. It might be a problem in the future. Please tell us about it. And yeah, that's actually very easy to accomplish because the default state of our static code analysis program is to only do the related data flow, meaning that it will not care if you throw the exception at the beginning. It will still tell you about the danger on the xcall spawn line. So you can turn this on and off pretty easily. So that's one advantage that we have for this modular design, where the related data flow is treated differently from the local execution flow. It's not intermixed. So it's not like, oh, I need to guess all these conditions and then do the tracing. No, we do all of the tracing, and the conditions are used to improve the results after the fact. So on the right, we have a method that has this condition, right? So it could be true or false. But look here, you can tell that something interesting is happening. Whether it's true or false, we will return 100 or we will return 0. If we're returning in both cases, then no matter what, the xcall spawn of danger at the bottom of the method is not going to happen, right? So that's another thing we could omit if you wanted to omit it. So we could say that, hey, it doesn't matter what the condition is, whether it's true or false or whatever, then you always return a number and you never get to the bottom of that method. So in that case, we could just say, don't care about the last line of that method because it's not important right now. And of course, if you would like to see everything, we could turn this feature off. Then you will see everything, including the thing that's right after the condition that always returns. So we could do limited prediction of branching in loops. And so for very complicated scenarios, it may not always be possible to give you like a great answer. The worst answer we could really give is maybe. So for example, if you have some very complicated situation and there appears to be some dangerous thing happening in the middle, we will report it and say, maybe this will happen. It might happen. It could happen. We're not sure. But for other simpler situations where the code is more structured in a way that we can make inferences about it, what we're going to do is say, hey, this definitely can't happen. This statement definitely can't happen. It's not reachable anymore. So that is valuable information for you because if you get 10,000 vulnerabilities, which it may not be that number, it may be much smaller. You may get no results or some results, but we want to reduce the noise in those kinds of results if you do get results. And reducing noise is valuable because it saves you time and allows you to focus on the things that are important to you that are actually out in the wild rather than just being a part of the code that is not reachable yet. So we've talked a lot about tracing. We have talked a lot about security issues. And so what else can this do for us, right? So static code analysis can be used for a lot of things that are not, security vulnerabilities, that are not related to OWASP, the list of OWASP problems in applications. So the first thing you could do is find all the unused routines. So you run your program and you're wondering what code is not being used, what code is never getting called. So again, you could do this manually. You can even do this in Visual Studio. You can find all references on a function or a subroutine. And what happens is that if you don't find any references, then it was never used. So then you can most likely just get rid of it. It will still be in source control, but it doesn't need to be in the production environment. But what if you just want to find them all at once? Well, that's actually something that static code analysis can do. We start with the main routines. So whatever the entry points to your program are. So when you start with main is where your code starts executing. And then main will call into other functions. So we just trace all those functions, trace all the functions that are called from those functions, and so on and so forth. And then whatever is left over is an unused routine. So those unused routines never get called. They never get used. You can still keep them around in source control, but if you delete them from the code, then your production environment is cleaner, it's more maintainable. Your developers don't have to worry about code that is not getting used. Makes the code smaller. Smaller code is always more maintainable than really bigger, messy code. Speaking of messy code, we can find monolithic logic or unmaintainable logic. So there could be parts of your code that are extremely well written, that's robust, it's been well tested, it's maintainable, and it's easy to understand and read. Other parts, not so much. Okay, you may have like some parts that are more like spaghetti code, where the code looks like a giant ball of spaghetti and you cannot tell what is going on at all in the code. So if we can find these areas, what you can do is refactor them. You can rewrite them, make them more maintainable, test it properly, and make it better. Modernize your legacy code. That's what we're all about, modernizing legacy code. Detecting unsafe memory operations. So what does this mean, really? So memory operations as in freeing memory. So if you use memproc, you allocate memory, you can resize memory, you can free memory. What if you forget to free the memory, or you allocate the wrong size, or you resize it incorrectly? Those kinds of things, you want to know about them. Those are hard to get correct. There have been entire systems like garbage collection, reference counting, other things that deal with this, right? Like, this is a huge problem. Humans can never get it right, apparently. So we need systems in place to make it easier for us to tell, should I deallocate this? Should I allocate this part? So if you're still using memproc, then we can help you detect anything that's not safe with how you use memory allocation, and then hopefully give you a path to fix those issues and have a memory safe program. And another thing is determining what needs to change when you resize a field. Field resize is a bit complicated in Synergy. So if you have alpha that's 10 characters long, you want to change it to alpha, which is 15 characters long. So that's going from A10 to A15. So when you do this, the problem is that it changes the size of the enclosing record, and it changes a bunch of other things. And you would really want to know everywhere that you need to change, but there could be thousands of places. So once that happens, then what do you do, really? So static code analysis can go in there, find the places you need to change, and tell you, hey, these are the places you need to change them. Can even tell you about issues such as alpha truncation. So when you resize the field, you may fix all the compilation errors that are the result of that, but you might not fix some of the runtime errors, because alphas can get truncated silently on Synergy, right? So when you assign a field to another field, that alpha could get truncated, and you do not get an error for this, meaning that you think you solved the problem, but actually you missed a part. So to avoid missing the part, you can run static code analysis, and it will tell you, hey, you might be missing this part. It might get truncated here. We can actually detect truncation just by tracing the integers that are involved in all the ranges, the relative ranges, the overlays. Tracing the integers gives us information about how big those alphas are, or how big they will be at runtime. And so when you do this, then you have a wealth of information for being able to resize that field. And this turns a hard problem into a somewhat easier problem in the future. One thing I would like to say about running this tool, so when you finally get to run this tool against your own code, it's possible that you will get many results, or you would get 0 results. If you happen to get 0 results, that's not a bad thing, because it just means that with the current capabilities of our tool, that we were not able to find any security issues that are currently in your code. Now, that doesn't mean there are none at all. It could mean that there's some lurking around, and we need to improve the tool to make it better to be able to detect those kind of things. But just knowing if you get no results, it just means that there are currently no security issues to fix at that time. So now, taking questions from the audience.
Thank you, Oliver. That was great. All right, let me see. My chat went away, so let's see. Okay. Wow, we have some good questions from everybody. Thank you all for being awake with us. All right. Tony asks, can this be run on a traditional Synergex DBL system that is run and stored on OpenVMS development cluster? We are currently upgrading and integrating our system, and we'll be moving to Visual Studio in the future.
Yes, you can run it on traditional Synergy. It doesn't matter if it's VMS or Linux or Windows. The tool is designed to work on both Synergy.net as well as traditional Synergy. So it should be possible to do that. And the interesting thing, you mentioned moving to Visual Studio. So it would be nice if people would move to Visual Studio, because the way the code analysis, the static code analysis currently works, is that we take a Visual Studio solution file that has Synergy projects in it, and we process that in order to do the analysis. For now, this is actually a necessary step for the static code analysis, but we will look into whether or not we can do essentially the same thing if you're not using Visual Studio. So as long as we have all the code and we know how to build it, and we have the instructions for building that code, it should be possible to do the static analysis even without the Visual Studio solution. But if you are using Visual Studio, it's a much nicer experience, and it'd be a lot easier for you to actually run the static code analysis since it operates on the solution files.
And I knew someone would ask this, David Blackburn. When will this be released? And I'll take the answer to that. It is by the end of next year. But David, it sounds like you're signing yourself up to beta test, so I'm gonna keep that in my mind. And all right, I've got a couple other questions. Will this static code program work on both traditional Synergy and Synergy.net?
Yeah. We mentioned that earlier, where it doesn't matter if you're using the .NET side of Synergy or the traditional side of Synergy, because the tool is designed to work on both systems. And what we've done is that we actually have the same code base for most of the stuff, but for specific features for Synergy.net, then we would have like special cases for those kinds of things.
It looks like we've got a lot of beta test volunteers here, so I don't think I'll have to beg anyone to help us with that. Oliver, you mentioned Windows and Linux as possible targets for security breaches, but what about OpenVMS? And I actually there's been a couple customers that have had security incidents, and the VMS, they always call their applications alpha, and the alpha systems are always untouched, and everything else gets compromised. So Oliver, what's your take on that?
Yeah, I think what you're talking about is, if I'm understanding correctly, that the VMS system becomes untouched and everything else is compromised. So that's really interesting. Meaning that on VMS, if you're using VMS, it's unlikely that a hacker would know how to use VMS in the first place, because there's a less like surface area and people are not as familiar with it. But that doesn't necessarily make you safe. So if there's a hacker that specifically targets your own code and they really want to get your private data out of that code, then they can figure out how to use VMS, and then they can send you dangerous data that could operate on VMS. So you're not exactly safe on VMS just because it's less used, but you would still need to worry about this in that case. So this is where the tool can help you with that.
Hi, Rachel Blunden. She's asking, what about AIX7?
I'm not entirely familiar with that, but
it's kind of like Linux, but not. That's my understanding.
So it shouldn't matter what the system. It doesn't matter what system you're using, as long as it's code like Synergy code, whether it's traditional or .NET, then we should still be able to analyze it, because we don't depend on the operating system. We're not running the code. We're just looking through all of the source using an automated system and trying to make guesses about what's going to happen. So it doesn't matter what the operating system is or what platform you're on.
I think she meant like, are you less likely to get hacked if your app is on AIX? Are you less likely to get
hacked on AIX7?
Like how OpenVMS, it's less likely. Is it also less likely on AIX?
I think that's a very similar situation where the less used the OS, the less likely you are to get hacked. But if there are other places that are easier to compromise, then it should totally be possible to, at least some of the systems you have might be unsafe in that case.
Yeah, we'd still love to get that customer to Linux. But
getting to Linux is a good idea.
We can dream. We can dream. All right. What other kinds of security issues on the list are you planning to support or not support?
So yeah, what other kind of security? So the list is called OWASP, the OWASP list of vulnerabilities. So you can just search for OWASP on Google or whatever, and it will give you this big list of things. So the things that we're not going to support are language specific stuff. So language specific stuff is like anything that only applies to Java or only applies to PHP. Those are not vulnerabilities we're concerned about. But anything else that is for general programming languages, including Synergy, anything that applies in general, like invalid memory, management or buffer overruns or uh, data injection, those kind of things that apply to every language, we will want to support essentially all of them with our static code analysis. So some may be harder to support than others, but we will incrementally give support to all of the things on the list that are not tied to a non-Synergy language.
Gordon, yes, I also see a ghost in Oliver's background.
Yes.
It is almost Halloween, after all.
It is part of the wall, and I'm not sure why it's there, but happy Halloween.
Well. Happy Halloween, everyone. All right. So thank you, Oliver, for that awesome session, and hope you keep busy. Okay. All right, Dustin. When this is released, is it planned to be an additional cost? Well, yes, it is something we will charge extra for. And if you want more information on that when the time comes, let me know. Good question. So thanks, Oliver.